Okay, so last this lecture and lecture tomorrow, we are going to focus on canonical properties of canonical modules. Properties of canonical modules. So remember, these are defined only for Cohen-Macaulay rings right now. So Rm will always be a Cohen-Macaulay local ring, and dimension of R is D. And if I don't specify, E will always denote the injective hull of the residue field. Of the residue field, K equal to R mod M. And a module, an R module C is called a canonical module for R if it satisfies three conditions. C is a maximal Cohen-Macaulay R module. This means that the depth of C equal to dimension of C equal to dimension of R. Okay. The second property we demand from C is that its injective dimension of C is finite. And so we know that once it is finite, the injective dimension is actually equal to D. Okay. And tomorrow, as a consequence of our study of canonical modules, I will show you an injective resolution of C. Okay, it's one of the, very, very pleasing injective resolution. It will come out as a consequence of our understanding of canonical module. The third condition is like a rank condition, and it is that the type of C, which is the dimension over the residue field of d text of K C is 1. Okay, among all the xi of Kc, there is only one non-vanishing x, namely this t text, and it is a vector space over K, and it is non-zero vector space. So we demand that its dimension is 1.
We can't see you, Joel.
Pardon?
It's not visible.
So the slide is not visible?
No.
Now?
Yeah, now it's visible.
Okay. It's really tough. I think what I see is not exactly what is on the computer. Okay, so there are three conditions. It's a maximal Cohen-Macaulay module of finite injective dimension, and the type is 1. Okay. So the question before us are, does there exist such a module? Does there exist such a module? So I will not, due to lack of time, I will not give a necessary and sufficient condition. The necessary and sufficient condition, okay, you can read from any book. It says that there exists such a module, there exists a canonical module if and only if R equal to S mod I, where S is a Gorenstein ring and I is an ideal of S. Okay. So just now you heard a lecture on coin structure theorem, and it said that if you have a complete local ring, it's a homomorphic image of regular local ring. Regular local rings are Gorenstein. We have proved that. And so complete local rings, which are Cohen-Macaulay, will always have a canonical module. Okay. And many properties of a local ring, they go back and forth to its completion, because R to R completion is a flat local homomorphism. Okay. So this is not such a restrictive condition that it is homomorphic image of a Gorenstein local ring. You complete and then this condition is satisfied. Okay. I will not prove this. Proof is not difficult. In fact, in one exercise, the proof has been done already in dimension 0. By using the idealization, we saw that if you take idealization of the injective hull, it's a Gorenstein ring. Okay, and the given Artinian ring is a homomorphic image of this idealization, which is a Gorenstein ring. So in dimension 0, we have already done this, and the general case can be reduced to this. So I'm not going to prove this existence criteria. The second result that we will prove, that if it exists, then any any two canonical modules C and C prime are isomorphic. Okay, so we can talk about the isomorphism class, and therefore we can use a notation. So omega R will represent the isomorphism class. Or the up to isomorphism, there is only one canonical module if it exists. So a lot of research which is ongoing is about computing the canonical module, because it reveals a lot of information about the given local ring, Cohen-Macaulay local ring. We are going to do canonical modules for local rings, Cohen-Macaulay local rings, but there is a exactly parallel theory for canonical modules of graded Cohen-Macaulay rings. So graded Cohen-Macaulay rings arise when we look at the homogeneous coordinate rings of projective varieties. And there one constructs the canonical module, and similar criterion exists. So one has to redo the whole thing for in the graded category, but the exactly same proofs go through in the graded category also. Okay. So in the first attempt, we just do it for local rings. Okay. Then then we will once it exists, we will get a explicit construction, explicit formula for canonical module. In terms of text. Okay. So this I have briefly done this when I introduced Grothendieck's approach to Gorenstein rings. Remember, if the Gorenstein rings were defined in the special case when we have a regular local ring quotient by an ideal, and suppose this is Cohen-Macaulay. If this is Cohen-Macaulay, then once it is Cohen-Macaulay, then the projective dimension of S over I, S is height of I, okay? And so it has a minimal free resolution whose length is H, and We also saw that S mod I is Gorenstein if and only if beta H is 1. And among all the X, the only non-vanishing X of S mod I and S is this X, and this is called the canonical module of S mod I. Okay, that was Grothendieck's definition. And we will see as a consequence of this new definition of canonical modules that this old definition of canonical module is exactly the same as the new definition. This is an explicit construction of the canonical module. It is abstractly defined as a module of, as a maximal Cohn-Macaulay module of finite injective dimension whose type is 1. But we will see that in this special case, when the ring is homomorphic image of a regular local ring, this is the canonical module. Okay. Yeah. So this is the plan, and if I have time, I will come back and use all this theory to do the converse of the Gorenstein property of R mod I. I mean, Gorenstein property of a one-dimensional Cohn-Macaulay local domain in terms of the co-length of the conductor ideal. We proved one direction that if a one-dimensional Cohn-Macaulay local domain is Gorenstein, then the length of R bar over R is same as length of R over the conductor ideal. But this is also a sufficient condition. And to prove that this is a sufficient condition, we will need all these results about canonical modules. In the modern proof, of course, you can read a paper of Kunz, where he doesn't use any homological algebra or canonical modules, but gives a proof using elementary means. Okay. All right. So this is the plan for today and tomorrow. I want in many places I'm going to use some parts of mathless duality. And I will give a generalization of mathless duality in arbitrary dimension. Okay, so mathless duality has to do with duality with respect to the injective hull. So this applies to Noetherian local rings. And suppose E is the injective hull of the residue field. So this is a Noetherian local ring, where E is the injective hull, and let us denote N, R, and suppose this is complete also. There is a statement for non-complete local rings. One can easily write. Okay, so NR denote the category of Noetherian R modules. Is a category of Noetherian R modules, and AR denotes the category of Artinian R modules. Okay, so Noetherian R modules and Artinian R modules, when you first look at their definition, they seem to be dual notions. But very soon we start coming across properties which are completely different. Artinian local rings are zero-dimensional, but that is not the case with Noetherian R modules. The injective hull here can be used to connect these two categories. That is, Artinian modules, they can be used, but using mathless duality, we can go back and forth between these two categories. Okay, so then there is the statement says that there exists an anti-equivalence of these categories, which means there is a functor which reverses the arrows. Okay, so this functor is established by taking Hom into the injective hull. So on one side, we have all the Noetherian modules over these complete local rings. and we want to produce an Artinian module from a Noetherian module. So take this Noetherian module and map it to HOM R M E. E is the injectival of the residue field. We will write this as M check. Okay, M check. And so because this is taking M into HOM ME, this is a contravariant functor. Okay, and E is an injective module. So this is exact sequences will be mapped to exact sequences. Okay, the reverse map is also same. Takes an Artinian module and maps it to M dual. I mean N dual. And this is a duality. That means if you start with M and map it to M dual and come back to M check, M double check, it is naturally isomorphic to M. So what a field does to finite dimensional vector spaces, the injective hull of the residue field is doing the same thing. Yeah. So this is the statement of duality, mathless duality. It has one more part, that if I restrict in this category of Noetherian modules, there are, look at the finite length modules. So finite length modules, they are Artinian. So the finite length R modules are forming a subcategory of NR as well as AR. So if you restrict this functor to finite length modules, then the length does not change. That is, length of a finite module is same as length over R of its L check. Okay, and HOM R EE, that is the endomorphism ring of the injective hull, is isomorphic to R. So R was complete. If we look at incomplete local rings, then endomorphism ring of E will turn out to be the emetic completion of R. Okay, yeah, endomorphism ring of the injective hull is the completion of R, but in this statement of mathless duality, I'm assuming that R is a complete local ring, so this is equal to R. Okay, so this is the statement. This E, the module E, has some properties. I will list them. We will be using these properties very often. Properties of E. First of all, it is a faithful R module. The annihilator is 0. Second, its Sockle dimension of E. Sockle dimension of E. Okay. It's a vector space over K is 1. Okay. And E is an Artinian module. E is Artinian. R module. And we have seen that if you have finitely generated injective module, then the ring is Artinian. Okay, so if you go out of Artinian local rings, then this injective hull is a huge module. It is not finitely generated, but it is Artinian. Okay. All right. So these are the preliminaries. We have done a few of these things when Sudeshna discussed some of these things. But I advise you to read the proofs in Bruno Sergeau. Within 3 pages, they have finished all the proofs of mathless duality. It doesn't require anything, completely self-contained. So because of lack of time, we will proceed without proving this. We will use many parts of mathless duality in the theory of canonical modules. Okay, so there was one preparatory lemma that I proved last time. Let me recall that. So suppose M and N are R modules. These are uh, finite R modules. And X bar, this is N regular. This is a N sequence, N regular sequence. Okay. So there is an induced map, phi bar from M mod X M to N mod Xn. And this lemma says that if this phi bar is isomorphism, phi bar is R mod XR isomorphism, then phi is also an R isomorphism. Okay, this proof we did last time, right? By using induction on the number of elements in the sequence and using the snake lemma. Okay, so we will keep using this lemma to construct isomorphisms of canonical modules. We want to prove that any two canonical modules are isomorphism. The way we are going to do is we will apply induction on the dimension. I mean, canonical modules are maximal Cohn-Macaulay modules, and any homogeneous, any system of parameters in the local ring, the base ring is also Cohn-Macaulay. So if you take any system of parameters in the Cohn-Macaulay local ring, it is going to be a regular sequence on the canonical mod on any canonical module. Okay, and these properties, the three properties that I listed of canonical modules, they get transferred when we go mod regular sequences. So we can reduce many of these statements to dimension 0. Okay, and in dimension 0, we have nice statements for mathless duality, and that does the job. But we have to lift the isomorphism back to arbitrary dimension, and that's where this lemma is useful. That after going mod a maximal regular sequence, we get modules which are finite modules or Artinian local rings, and there we employ the mathless duality and then lift the isomorphism back to the original ring. Okay, that is the strategy here. Okay, all right. So let us proceed step by step. Okay, so we start proving this uniqueness will come in several steps. This is one of the steps. Okay, so suppose, yeah, so let C be a maximal Cohn-Macaulay R module. So I have fixed my ring. RM is Cohn-Macaulay, local dimension of R is D. This is a standing hypothesis. And take a maximal Cohn-Macaulay module. Remember, canonical module has to be a maximal Cohn-Macaulay module. So let us see how much we can do if you just assume that it's a maximal Cohn-Macaulay module. Yeah. So right now, just assume it's a maximal Cohn-Macaulay module, and X bar. If I take X bar to be a system of parameters in R, it will be a regular sequence on the maximal Cohn-Macaulay module also, because it is a system of parameters for the module too. And once I take a Cohn-Macaulay module, every system of parameters is a regular sequence. Yeah. So rather than taking system parameters, just take an R sequence. And by this remark which I just made, any R sequence is also going to be a C regular sequence. It will be a regular sequence on C, because I can complete R sequence to a system of parameters, and then this system of parameters will be a regular sequence on C. And so this part of the regular sequence will also be a regular sequence on C. Okay. So X bar is an R sequence. So it could be just one regular element also. Okay. Right. Okay. Now, first property that so let me make a notation instead of writing it again and again. So CMT This is the set of Cohen-Macaulay R modules of dimension T. Okay, since these are modules over R and R has dimension D, T is less equal to D because it's the dimension of R over the annihilator. Okay, so CMT is the class of all Cohen-Macaulay modules of dimension T. Okay, now first statement says that if M is in CMD, that means it is a maximal Cohen-Macaulay module. Okay, and all the X MC are 0 for all I bigger than equal to 1, then when I take HOM R MC, it is again a Cohen-Macaulay module of dimension D. So maximal Cohen-Macaulay modules are mapped to maximal Cohen-Macaulay modules. If I take HOM into C, which is itself a maximal Cohen-Macaulay module. That's what it says, but with this condition that all the higher X are 0. So that is an assumption. Okay. Now this assumption X I MC is 0 is satisfied when C has finite injective dimension. Okay, we'll see that in a minute. So this is not an artificial condition. Canonical module satisfies this condition. Okay, so the maximal Cohen-Macaulay module is mapped to maximal Cohen-Macaulay module when I take HOM MC. Okay, that is the first statement. The second, if the injective dimension of C is finite, okay, then we can generalize this statement. That is, take all Cohen-Macaulay modules of dimension T, and when I map them using the HOM functor into C, it also lands in CMT. Okay, so first statement was for maximal Cohen-Macaulay modules, but the second statement, when we put this additional condition that the injective dimension is finite, then this statement is valid on all Cohen-Macaulay modules of any dimension, that CMT is mapped into CMT by HOM. Okay, so both 1 and 2 will be valid statement for any canonical module, because canonical modules have finite injective dimension. Not only that, in this case, in case 2, if we look at X I R MC, then this is 0 for all I not equal to D minus T. And if we take X D minus T, this is not HOM. This will be, sorry. Yeah. So I want to produce a Cohen-Macaulay module of dimension T using in some analogous process as we did in number 1. Okay, in number 1, all the X's were 0. Okay, for I bigger than equal to 1. But if I take Cohen-Macaulay module of dimension T, then among these Xi, there is only one non-vanishing X, namely the D minus T X, okay, of MC, and this is what goes into CMT. Okay, so T-dimensional Cohen-Macaulay module is mapped to T-dimensional Cohen-Macaulay module. If I, instead of taking HOM, I take D minus T text from M to C. Okay, that is the module. So if so, the first case is a special case. First statement is a special case of second for canonical module, because I take D equal to T, then this is simply the HOM MC. Okay, and so HOM MC produces a maximal Cohen-Macaulay module from a maximal Cohen-Macaulay module. Okay, so this is the first statement. Yeah. Okay, so these two statements are absolutely essential to prove uniqueness. Okay, so let me begin. The first statement for D equal to 0 is clear. Suppose D is equal to 0. Okay, if D is 0, then R is Artinian. Okay, R is Artinian, and C is a finite R module, M is a finite R module, and the first statement says that Hom MC, whether it is a Cohen-Macaulay module of dimension 0, of course, Hom MC is annihilated by some power of M, because some power of M is 0 in Artinian ring, and annihilator of individual modules in Hom, their annihilators are also in the annihilator of the Hom. So annihilator of this contains Mn, okay, and this implies that Hom R Mn MC is also Artinian. It is finite, and it is annihilated by M to the N. So it is in fact a finite length module. It is Artinian, and so first statement is okay for D equal to 0. So we may assume that D is positive. We may now assume D is bigger than or equal to 1. Okay. Once D is bigger than or equal to 1, C is maximal Cohen-Macaulay module of dimension D, which is bigger than or equal to 1, and therefore there exists a C regular element. There exists a C regular element call it X. Okay, there is a C regular element, call it X. Yeah, and so we are applying induction on the dimension of ring. So we want to reduce to lower dimension, and so look at this exact sequence. X is also regular on C because C is a maximal Cohen-Macaulay module. So we have this exact sequence. Okay, and we are trying to wonder what kind of module is MC. Okay, is it also a maximal Cohen-Macaulay module? And we are given this condition. We are given this condition that XIR MC is 0 for all I bigger than or equal to 1. We are given this condition, and then I want to show that Hom MC is a maximal Cohen-Macaulay module, and we have our induction hypothesis. Okay, and this exact sequence. So how to bring in Hom MC? Just apply the functor Hom R M M dash. So this is a covariant left exact functor. So there will be a long exact sequence of the X. Okay, but all the higher X are 0. And so this exact sequence is being converted into exact sequence. Okay. Yeah. So yeah. So we get 0 to Hom R MC to Hom R MC, and this multiplication map induces multiplication map here. Okay, yeah, and then we get Hom R M C mod X. Okay. So I have just one regular element that gave rise to this short exact sequence, and because higher X are 0, this sequence is exact sequence. So the next module is X1 of MC, which is equal to 0. Okay, so this means that this last module is co-kernel of this previous map, and therefore Hom R M C mod XC is isomorphic to Hom R MC over X times Hom R MC. Okay. Yeah. So, but this right hand side is obtained when I take the tensor product. Hom R MC tensor with R mod X. Yeah. Okay. And we have right. So, but yeah, now look at this module. Look at this module. Hom R M C mod XC. Okay. This is equal to Hom R M C mod XC is Hom R mod X. Okay. Then R mod X comma C. C mod XC. C mod XC is Hom R mod X, R mod XC. And now I use the Hom tensor adjointness. So I have two rings, R and R over X. And the module M is R module, but C mod XC is R mod X module. So these rings get changed when I apply Hom tensor adjointness. So this is Hom R mod XR, okay, M tensor R mod XR to C mod XC. Okay. Yeah. So this is, yeah. So this last module is just Hom R mod XR, M mod XM, C mod XC. Okay. So what we have, yeah. So now by induction it follows. Okay. This follows by induction because the dimension of R mod XR is one less, and C mod XC is a maximal Cohn-Macaulay module on R mod XR. Okay. And the X condition is also satisfied by change of ring principle of Rees. Okay. Yeah. So by induction, this Hom RMC. Okay. This is in C Cohn-Macaulay modules over R mod XR. Okay, of dimension D minus 1. Okay. But look at this exact sequence. Look at this exact sequence. Okay, this exact sequence that says that this module is obtained by this module is same as Hom R MC mod X times this. Okay. So but this X, because of this exact sequence, X is a non-zero divisor on Hom RMC. Yeah. This exact sequence says that X is a non-zero divisor on Hom RMC, and this module is homomorphic image of Hom RMC by going mod a non-zero divisor on this module. Okay. But by induction hypothesis, Hom M mod XM C mod XC is a maximal Cohn-Macaulay module over R mod XR. Okay. Therefore, okay. So this module is also maximal Cohn-Macaulay module over R, because over local rings, M mod X is Cohn-Macaulay if and only if M is Cohn-Macaulay module. So that shows that HOM RMC is a maximal Cohen-Macaulay module. Is this clear? Any questions? Let me try to reconnect. I think the net connection is better now. Any questions on this?
Yes, sir.
Yeah.
How HOM M comma C mod XC is equal to HOM of M comma I think that is R mod X comma C mod XC.
Yeah. So just 1 minute. Yeah. What is your question?
Sir, I am asking the second last equality of the left hand side page.
Yeah. Why it is
How
exact?
R mod X is exact. I mean, I got disconnected in between, so I didn't listen to this part.
Yeah. So C mod XC, see, we had this exact sequence on this slide 7. You have this exact sequence C to C to C mod XC. X is, I'm picking X to be a regular element on C. Yeah, there exists a regular element on C because C is a maximal Cohen-Macaulay module. If I take any regular element on R, it is regular on C. Okay. Yeah. So
Yes,
so
sir.
this, yeah. So apply HOM M dash on this sequence. Then I get this sequence in this area. HOM MC, HOM MC multiplication map, and so HOM R M, and because the higher X are 0, HOM R M comma C mod XC is the co-kernel of this previous map.
Yes, sir. Yes, sir.
Okay. But then I use this HOM tensor adjointness to see that HOM R M C mod XC is isomorphic to HOM R mod XR, M mod XM, and C mod XC.
Okay.
Yeah, there is a simple HOM tensor adjointness.
Okay.
So, but by induction, this HOM R mod XR, M mod XM, C mod XC is a maximal Cohen-Macaulay module over R mod XR.
Yes, sir.
Because the X is also specialized by Rees theorem, change of ring principle on X. Okay, so this is a maximal Cohen-Macaulay module, and so therefore, but then this is equal to HOM R MC over X times this, and this exact sequence here, it shows that X is a regular element on HOM R MC.
Yes, sir. Okay.
Right. So it shows that HOM R MC is also a maximal Cohen-Macaulay module. Because if homomorphic image of MCM is MCM, then the module is also MCM.
Yes.
Yeah. Okay. So this was a way of producing maximal Cohen-Macaulay module from maximal Cohen-Macaulay module by taking HOM into this maximal Cohen-Macaulay module C. See, we are going to compare two maximal Cohen-Macaulay modules, that is two canonical modules. Both are maximal Cohen-Macaulay modules. Okay, so we must have, and we want to produce a isomorphism between them, and we will apply induction, okay, to produce this isomorphism. So that's what this is, a preparation for that. Right now, it's not clear. Okay, so this was part A. In part B, we want to generalize this to Cohen-Macaulay modules of any dimension. Okay, so now we take M to be Cohen-Macaulay module of dimension T, and T can be 0 up to D. Okay, take such a module, and we want to show that we can do similar thing to produce a Cohen-Macaulay module of dimension T somehow. Okay, now in this part, we are assuming that the injective dimension of C is finite. So we are invoking the second property of canonical module. Injective dimension is finite. Okay. Once injective dimension is finite, then we know that this injective dimension is equal to depth of R, but R is Cohen-Macaulay, so therefore this injective dimension is D. Okay. Now recall this great formula: depth of n plus supremum of I, so that x I R and M is not equal to 0. Remember what this was? Can anybody recall what this is?
Injective dimension.
Injective dimension of M.
Right. Injective dimension of M. So in this formula, we put M equal to C and N equal to M. Okay. What is depth of M? In this case, depth of M is, because M is a Cohen-Macaulay T, and this number is D. Okay. So that says that if I take X I R N M, this is 0 for all I bigger than what number? D minus T, right? X I N M, X I M, sorry, X I M C. X I M C is 0 for all I bigger than D minus. Is this clear? Is this clear to everyone? Why X I M C is 0 for I bigger than D minus T?
Yes,
Srikanth, is this clear to you?
yes, sir.
Yeah, I'm just substituting. Okay. This is a very useful formula. But now I want to show the lower x are also 0. So can you tell me why the lower x are 0? This x MC, for I less than D minus T, they are also 0. Why is that?
Ishibek vanishing.
Exactly. Ishibek's theorem says that you take depth of C minus dimension of M. Then these x's are 0 for I less than this number. But C is a maximal Cohen-Macaulay module. So this is D and dimension of M is T. So for I less than D minus T, all the xi is 0. For I bigger than D minus T, all the x are 0. And why do you think that the D minus Tth x is non-zero? Can anybody tell me why D minus Tth x is non-zero? Why this module is non-zero?
Supremum of
Yeah.
because supremum of that means supremum of I where that is non-zero is injective dimension of C minus depth of M.
Right. So that is built into the formula. This is non-zero. Okay.
By
Yeah.
that.
Yeah. But you see, you can also see it by looking at the annihilator of M. Okay. What is the height of the annihilator of M? M is dimension T. What is the height of annihilator of M? Dimension of R over annihilator of M. This is dimension of M.
Okay.
This is T.
Yes.
So what is the height of annihilator of M?
D minus T.
D minus T. And annihilator of M is in the Cohen-Macaulay ring, right? It's an
So it is
ideal in
equal to the
Cohen-Macaulay
grade.
ring.
Yes.
So grade is also D minus T. Okay. And this regular sequence will be regular sequence on C because C is a maximal Cohen-Macaulay module.
Maximum Cohen.
So annihilator of the first module contains a regular sequential length d minus t on the next module, and it cannot contain regular sequential length bigger than d minus t because its height is d minus t, and therefore by the depth characterization, this d minus t, the x of MC, is also non-zero. This is another way of seeing that, right? Is this clear? Yeah. So among all the xi of MC, this is the non-zero module, only non-zero x. Okay. So let us show that this non-zero x is also in CMT. It's a Cohen-Macaulay module of dimension T. So we started with a Cohen-Macaulay module of dimension T, and by taking x d minus t r MC, we are producing a Cohen-Macaulay module in the same set. Okay, and this is obviously a generalization of part A, because in part A, d equal to t, and we proved that Hom MC is 0. And when d equal to t, all the higher x1, x2 of MC, they are all equal to 0 by this depth n and injective dimension of M formula. So part A is clearly a special case of part B, but let us see that part B actually follows from part A. They are more or less equivalent. All right. So we want to show that it's a Cohen-Macaulay module of dimension T. And so we will apply induction. We will apply induction on T. See, the proofs in this, the object look complicated, but the proofs are very logical. Once some number is there which is related with depth or projective dimension, you just try to apply induction on that number, and those numbers nicely go down when you reduce the dimension. So, we started with a Cohen-Macaulay module of dimension T, and I'm applying induction on that T. Okay, so suppose T equal to 0. If T equal to 0, then what happens? Then this M is 0 dimensional. Dimension of M is 0. So M is Artinian. M is Artinian. So look at XD R MC. If M is Artinian, it is annihilated. It's a finite module. M is a finitely generated Artinian module. It has finite length. Yeah, it has finite length. So some power of maximal ideal annihilates M, and the same power will also annihilate. Some power annihilates the X. But M and C are finite modules. So this is also a finite module. It is annihilated by some power of M. So therefore, this is Artinian. Artinian finitely generated module is Cohen-Macaulay of dimension 0. So this is dimension 0. So we are done for T equal to 0. Is this clear? XDMC is a 0-dimensional ring. 0-dimensional module. Can you hear me?
Yes, sir.
Yeah. I'm losing net connection. Okay. All right. So we are done with T equal to 0 case. So now suppose that T is bigger than or equal to 1. So this M is Cohen-Macaulay module, and dimension of M is positive. Okay. So there exists an X in M, which is M regular. Yeah. So this means I have an exact sequence m to m mod xm. M to m multiplication by x to m mod xm. Okay, and I'm trying to understand now the d minus tth x of MC. Okay, is it a Cohen-Macaulay module of dimension T? That is what we want to see. Okay, and we have this exact sequence. So what should we do? What should we do?
We can take the x
Can anybody
long exact sequence of
step?
x.
What should we do?
We can take the long exact sequence of x with respect to c.
Which functor we should apply?
Home dash c.
Hom dash. Yeah. So apply hom r dash c. This is going to reverse the arrows. Yeah, it will reverse the arrows. And here we know that below d minus t, all the x's are 0 of hom. X, I, and c are 0 below d minus t. So when you write the long exact sequence of x, then I will get 0 equal to x d minus t r m mod xm c. Okay, this will be 0, and then I'm going in this direction. So to hom, x r d minus t m c, then x r t minus t m c. Okay, this is multiplication by x, and then I get x t minus t plus 1 r mc, and then what will I get after this? Yeah, can you hear me?
Sir, after this, everything will be 0.
Yeah, that is because x I
because x
this is m mod xm. This is m mod xm, sorry, and this is
I
0.
greater than 0.
Yeah. So x d minus t plus 1 m comma c is 0. That is the next module. So this is 0.
Yes.
Okay.
Yes.
So this means that x r d minus t minus 1 of m mod xm c is isomorphic. Okay, it is isomorphic to, you see, this is 0. This has become 0, and this is the same module, and this is the multiplication map. So this module is co-kernel of the multiplication map on the same module. So it is x d minus t r m c over x times the same module. Okay. Now C is a maximal Cohen-Macaulay module. M mod xm has dimension d minus t minus 1. Its dimension is t minus 1. This module has dimension t minus 1, and C is maximal Cohen-Macaulay module, okay, of finite injective dimension. And therefore, this d minus t minus 1, this is the only non-vanishing x here, okay, by the same reasoning. And this module is homomorphic image of xd minus t by this element, and so that shows. But this is Cohen-Macaulay module, right? By induction hypothesis, this is a Cohen-Macaulay module of dimension t minus 1. So I have this finitely generated R module, and by going mod x, I got a module of dimension one less, okay, which is Cohen-Macaulay, and this x was regular. So this is a Cohen-Macaulay module of dimension t. This x, because this is 0, this multiplication map by x is a this is a x is a non-zero divisor on this module, because this is an exact sequence. Okay, multiplication map is an injective map on this module. Okay, so I have this element which is regular on this module, and this module is Cohen-Macaulay. So, and therefore I can lift it and get this Cohen-Macaulay module of dimension t. Is this clear? How induction has given. Any doubts on this? These are very subtle arguments. Yeah. Shall we proceed? Any doubts? See, I cannot see any participant, so you have to speak. So can you hear me?
Yes, sir.
Yeah, see, I don't know whether I'm connected or not. Okay, and screen is visible?
Yes, sir.
Yes, sir.
Okay, so now let's, we want to now prove that any two canonical modules are isomorphic, or if they exist on a Cohen-Macaulay local ring. Okay, so that is the result. So RMK is a Cohen-Macaulay local ring, and suppose, so let C and C prime be two canonical modules. Over same local ring, Cohen-Macaulay local ring. Okay. Then for any R sequence, X bar, maximal R sequence, X bar, it is a R sequence on both these maximal Cohen-Macaulay modules. And so part A says that C mod XC is isomorphic to injective hull of the residue field of R mod XR. R mod XR, this is an Artinian local ring. Yeah, because I took a maximal R sequence. So the R mod XR is Artinian local ring, and the residue field of this local ring is same as residue field of R. But this K is being thought of as a R mod XR module. Okay, so I'm taking injective hull of K over R mod XR, and this part A says that if I go mod this X, which is regular sequence on C, C mod XC is this injective hull. You see, so whatever maximal Cohen-Macaulay module I took, when I go mod XC, I get this injective hull of K over R mod XR. Okay, so on the right hand side, there is no C here. There is no C here. Right, so this is independent of C. Any maximal Cohen-Macaulay module will reduce to injective hull of R mod XR. I mean, of the residue field. Okay, and now we want to say that this fact actually implies we can lift this isomorphism back to C. C and C prime are isomorphic R modules, and the Hom R C C prime is isomorphic to R. And so so this is a cyclic R module. It is generated by one homomorphism. So any phi which generates, okay, which generates this is an isomorphism of C to C prime, right? So it says it's a cyclic R module. It's generated by a single homomorphism from C to C prime, but any generator is going to be an isomorphism from C to C prime. So there are plenty of isomorphisms between two canonical modules. D, the canonical module, if I take the endomorphism ring of the canonical module, okay, then there is a natural isomorphism from R to this, and this map sends R to multiplication by R from C to C. That is, X goes to XR. So R is isomorphic to endomorphism ring of C. That is a special case of part C. I just put C equal to C prime. Okay. So these are the properties, and essentially this is this statement, this theorem is saying any two canonical modules over a Cohen-Macaulay local ring are isomorphic, and there are plenty of isomorphisms, and the endomorphism ring is isomorphic to the ring itself. So let us prove this statement. Is this clear? We have done the preparation already in the previous proposition, because we use some of the properties of canonical modules in part A and part B. Okay, so proof. Proof of part A. Yeah. So C is a canonical module. So injective dimension of C is equal to D. Yeah, and when I go mod this maximal regular sequence, then then we have seen before that the injective dimension drops. This is equal to injective dimension. This is equal to injective dimension of C minus D. So this is 0. Yeah. This injective dimension is 0. So what can you say if a module has injective dimension 0 over R mod XR? And what about the type? What happens to the type of C mod XR? Type of C mod XR. Okay, this is equal to, this is C mod XR, because I have gone mod full, maximal regular sequence. The dimension has dropped to 0. C was dimension D, and X is having D. It's a regular sequence of length D. So this dimension is 0. So when we have dimension 0 module, to find the type, we have to take HOM, R mod XR, K, C mod XR. But by change of ring principle, by Ries's theorem, this is equal to XD R K C. Okay, and C is canonical module. Its type is equal to 1. So this dimension of D text of R K C is equal to 1, and this means that the type of C mod XR is also 1. Okay, but what is this HOM? R mod XR, R mod M, C mod XR. Okay, do you recognize what is this dimension? What is this module? This is equal to X XR colon M over XR. So this is equal to socle of R mod XR. So that says that the socle of R mod XR is one-dimensional. I mean C mod X. Sorry, what am I saying? C mod XR. If C was R, then this will be correct. So this is CX, XC. This is XC. X. Okay. So that says that C mod XC socle dimension is 1. So, but its injective dimension is 0. So I have injective module whose socle dimension is 0. Injective module. I have an injective module, let us say N, and its socle dimension. And so its dimension is N, dimension of N is 0, and socle dimension is 1 over Artin local ring. So what can you say about this module? Over Artin local ring. Pardon?
Yeah, by the decomposition of injective module, it should be equal to the E of K signal.
This is injective hull of R mod XR, no? So this N is isomorphic to injective hull of the residue field of R, right?
Yes.
The socle dimension tells you how many copies of the injective hull of K are there in the direct sum. And it's an injective module, and there is only one indecomposable injective module, namely the injective hull of K. So that's the situation we are in. So that says that this C mod XR, XC, this is its injective dimension turned out to be 0. So C mod XC is injective module over R mod XR of type 1, and therefore this is isomorphic to the injective hull of the residue field of R mod XR. And this says that C over XC is isomorphic to C prime over XC prime. Both are isomorphic to in the injective hull over R mod XR. So we are trying to produce an isomorphism from C to C prime. What we have got is an isomorphism from C mod XC to C prime mod XC prime. And we want to lift this. We want to lift this map to an isomorphism from C to C prime. Okay, so how do we do that? Yeah, but we have now both are maximal Cohen-Macaulay modules. Okay, and so therefore, by the calculation we did earlier, Hom C prime tensor with R mod XR, that is isomorphic to Hom R mod XR, okay, C mod XC, C prime mod XC prime. And this is isomorphic to Hom R mod XR. This is injective hull of R mod XR, injective hull of R mod XR over R mod XR. But matrix duality says that Hom EE over an Artin local ring is R itself. So this is isomorphic to R mod XR. Yeah. So here is my module. This is a Hom's, both are maximal Cohen-Macaulay module. So by part A, part B, this is a maximal Cohen-Macaulay module. Hom CC prime is an MCM. Okay. And this mod XR is R mod XR. Okay. So if I take tensor product with R mod M, I will get the same statement. So this says Hom R CC prime tensor with R mod M is isomorphic to R mod M. So this module is generated by one element. This is a finitely generated module over Cohen-Macaulay ring of dimension D, and tensor with R mod M gives me R mod M. So this is singly generated. This is generated by one element. This is cyclic module. This is cyclic module. So suppose let phi be a generator. Let phi be a generator. And I want to show that phi is an isomorphism. Yeah, I want to show that phi is an isomorphism. Any generator, any cyclic generator of form CC prime will be an isomorphism. Why is that? You see, I picked up this phi by using this using Nakayama lemma, okay, and one can use this phi by using this isomorphism R mod XR, okay, and this will be a generator of this module, yeah. So when I look at the cyclic module R phi, okay, this is a submodule. This generates C prime, okay, and when I go mod X, okay, this becomes an isomorphism, and this is a maximal Cohen-Macaulay module. So earlier we proved a lemma that if I have two finite modules, and I have a ring homomorphism, and x bar is a regular sequence on this module, and suppose I go mod this x, and the induced map is an isomorphism, implies that this psi is an isomorphism. That's the situation we are in here. This is a maximal Cohen-Macaulay module by part A, and this x bar is a regular sequence on this. And when I go mod x, I picked up this phi so that phi was generated mod x, okay, and therefore this phi. I mean this map is an isomorphism, okay. So R phi is isomorphic to Hom R C C prime. Yeah. So this is also a maximal Cohen-Macaulay module, because this is a maximal Cohen-Macaulay module. R phi is a maximal Cohen-Macaulay module. Yeah. And so that says that this R and R phi, they are isomorphic, because after you go mod X, R and R phi become isomorphism. But this was the isomorphism. After you go mod X, Hom MCC prime mod XR is R mod XR. So, and R phi mod XR is this after you go mod XR, and it is equal to R mod XR. And so I apply the same principle and see that R is isomorphic to R phi. Okay. Yeah. So that shows that this phi is an isomorphism. Because after going mod X, it is an isomorphism. So from R to R phi, it is also an isomorphism, because R phi is a maximal Cohen-Macaulay module. So this has many interesting consequences. Let me point out one consequence, and then we will stop. Okay. So we have proved that if canonical module exists, it is any two canonical modules are isomorphic of a Cohen-Macaulay local ring if they exist. Okay. So then since they are isomorphic, we will denote them by omega r. This is canonical module of Cohen-Macaulay local ring R. Okay. Then first statement, if X bar is an R sequence, then the canonical module of R mod XR is isomorphic to omega R over XR. Okay, because it's a maximal Cohen-Macaulay module. If you have an X is an R sequence, it is an R sequence on omega R. Okay, and this is saying that I can inductively construct a canonical module by going mod X, or test whether a given module is a canonical module. I can go mod a R sequence and then test whether it is canonical module over R mod XR. Okay. Second, so this is called specialization. Canonical module specializes. Then canonical module also localizes. So if I localize, suppose canonical module of R exists, then canonical module of R localized at P is canonical module of R localized at P. Third, this is a finitely generated maximal Cohen-Macaulay module. I can talk about its completion in the M-adic topology. Yeah, it is isomorphic to canonical module of R completion. Okay, so many times, if the ring is not complete, then we say a module is canonical module. Its completion is canonical module of R completion. R completion is a complete local ring, and by Cohen structure theorem, complete local ring is a homomorphic image of a regular local ring. No matter whether it is equicharacteristic or inequicharacteristic, a complete local ring is always a homomorphic image of a regular local ring, and we will see that in that case the canonical module exists. So if I am talking about a module being canonical module of an incomplete local ring, then I just complete it first and then see whether then it exists, and then identify with a canonical module of R completion. So I was saying, maybe you didn't hear this. If X is an R sequence and canonical module of R exists, call it omega R, then canonical module of R mod XR is omega R over XR. Okay. And canonical module of localization of RP is localization of the canonical module of R. And completion of the canonical module is the canonical module of completion. Okay. Now let's observe that why we are worried about canonical module, because it tells us when a ring is Gorenstein. R is Gorenstein if and only if canonical module is isomorphic to R. Okay. What are the properties of Gorenstein ring that we have done? Injective dimension of a Gorenstein ring is finite. It is equal to dimension of R. Then R is Cohen-Macaulay. And then the Sokal dimension of R mod a maximal regular sequence is 1. Yeah. So R itself satisfies the 3 conditions we have imposed on a module to be a canonical module. So R is isomorphic to omega R, because any 2 canonical modules are isomorphic. R itself satisfies the 3 conditions. And converse is also true. If omega R is isomorphic to R, then omega R has finite injective dimension, so R has finite injective dimension, and therefore it is Gorenstein. So in many concrete situation, this becomes a way of proving that a ring is Gorenstein. Calculate the canonical module, and if it is isomorphic to R, free of rank 1, then the ring is Gorenstein. So in this sense, the Gorenstein rings are the simplest Cohen-Macaulay rings, because their canonical modules are the simplest possible module you can think of, rank 1 free module. Okay, so our time is finished, and I will continue tomorrow.